away we go. Okay. All right. So this deals with problems in kinetic rate laws. Okay. First one is units of K for N204. They want to know what they are. Okay, so you're given rate equals empirically K onto N204, gas of course. I'll go ahead and put that in there if you would. And it is to the first, it's a first order reaction. Okay, and we need to solve that to find out what this is. Now, solving for K leads us to rate divided by the concentration of dinitrogen tetroxide to the first power, like that. So, any questions? Okay, and this is simply from the empirical rate law. Now, if you were trying to do a K value from a numerical, you would have a rate from your data table and concentration from the data table, plug them in and get a number. But here all we're asked to do is get the empirical units for this relationship. Rate is moles, molar, if you will, over liter second. Now you'll see problems that show up not only in molar but also in moles per liter second. So I'm going to do it in moles per liter second. Moles over liter seconds. We showed you that relationship during the quiz. So is everybody okay with that? This one? Okay, good. And this is moles over liters in the concentration term. Now I could have left that in molar and then have molar over seconds over molar, invert count, and have a reciprocal seconds in the end of it. But that would leave out the concentration term. It's acceptable, not acceptable, depending on the problem you're working, I guess. Invert and multiply to make this clear. We'll rewrite that one. Invert and multiply, liters over moles. Okay, liters will drop out, moles will drop out. Aha, still got seconds to the -1 are the only units that wind up in the K value. Now the K value is a proportionality constant. And therefore, as a proportionality constant, it could have some weird outcomes. I'm going to give you another one here. Here is an equation: 4NH3 as a gas plus 5. This is one like we had on our quiz. It goes to 4NO as a gas plus 6H2O as a gas, like that. Write the empirical rate equation. Is of course K onto NH3, and we learned, let's see if I can get that from the last. Okay, I'm going to save hypothetical reasons. This is first order, and this one is second order in oxygen. Hypothetically. I don't know because I didn't run any experiments to prove it. That's the point. The issue is you will come out with units of the K value different than you had. They don't always come out the same, is the point of issue. So K in this particular case is, and I write the denominator first, centralize everything, like that. And so this is mole over liter seconds. Here is mole per liter times mole per liter squared, and this of course goes to moles per liter seconds over moles per liter cubed, 3. Okay? Everybody good? See where I got 3? Just add the exponents. Yes? All right. Okay. So this translates to moles over liter seconds. I'm going to do 2 steps. I'm going to transpose this into the equation, invert and multiply, so liters cubed over moles cubed. Okay, so this now becomes liters squared, and this becomes mole squared. And so we finish with liters squared over seconds dot mole squared. Quite a bit different, huh? Quite a difference. So this is what proportionality constants can do to you. I mean, they can confuse the issue by looking weird. So in this particular case, yes. Okay, and these are used as you go through some of the problems. So be cautious and careful as you manipulate the units. Don't get in a rush, because sometimes it's easy to, and I've done it, not to invert and multiply and this kind of thing. So follow your algebra rules and stay ahead of the curve. Any questions on that? Okay, in which N2O4 is formed in the following reaction. Let's put it down here. Calculate the rate and then is formed in the following reaction at the moment in time when NO2 is consumed at this rate. This is a coefficient problem when you relate one side to the other. Okay, so we have 2NO2 as a gas going to N2O4 as a gas, and they want to know, calculate the rate at which N2O4 is being produced in this. So we simply set up our equation, change in NO2 gas over change in time to equal change in N2O4 gas over change in time. Now the coefficient in here is of course understood to be 1, and so we bring that over here, and the coefficient over here is placed in there at 2. Okay, so the NO2 is the one that is given, and it's 0.0592 mole per liter per second, and there is equal to 2 times your change in 204 gas over change in time. And so by solving for the unknown, we have 1/2 of the 0.0592 mole per liter per second, like that, and just to be sure without guessing. And of course that's 0.0296 molar per second. Very straightforward type problem. So you pair the one known, one unknown. Swap the coefficients, solve for the unknown. Okay. I'll try to leave that on there as I start the next one. Okay, now this next one is simply a derivation of NH3 and O2 are consumed, or even this one. It's all right, you've got 2 components in the reaction that are, one's known and one will be unknown. Right. Okay, so here is oxygen and here is of course water down here. So you want it, this kind of problem always comes in pairs only. So if you remember that. So when you have a coefficient type problem, it's only in pairs. So your equation is 4NH3 as a gas plus 5O2 as a gas goes to 4NO as a gas, plus 6H2O as a gas like that. And it's asking for a relationship between ammonia and oxygen. And then the second one is oxygen and water. And that's it. And anytime you work with a problem like this, it's coefficient in pairs, like that. So I'll do the oxygen, change in O2 over change in time is equal to change in H2O over change in time. So we're comparing oxygen and water. And what was the rule? Swap coefficients. That's all you have to do. Now one of them is going to be given, and one of them is going to be the unknown. So 6 being associated with the H2O, we'll put it over here, and the 5 we'll put right here. See how that works? We just switch the coefficient. Now again, one of them is going to be given. Look at that next problem here. Calculate the rate of formation of NO here and the rate of disappearance of NH3 for this reaction when the rate of formation of water, so everything has to be set up against water. So whatever you're working against, I'll do the first one. Okay. It's the same, looks like it's the same question. So you're given change in H2O, change in time is 0.04 molar per second. Okay, so they want nitrous oxide and ammonia for the first one. So it's a change in NO over change in time is equal to change in H2O over change in time. So water is 6, so we want to put it over here, and NO is a 4, so we want it to go there. And then they give you the water at that, so it's 4 times 0.04 molar per second, and so you have a little equation here that's in one unknown, and so it's a matter of solving for that one unknown. And so you see how it works now?
Yeah.
Okay, great. Anybody else? These are very important because I do give 2 or 3 of these on exam day. Okay. All right, so I'll let you fill in the blank, right? Okay, I'll go back. Okay.
Oh, no.
Hang on. Okay, we want to look at some of these rate law issues right here. In working with problems like this, the rules are straightforward in that you hold one constant and vary the other. That's the simplicity of how to deal with this in working with rate law determination. These kind of problems are determination of rate laws, okay? And essentially you hold one component constant and vary the other. Only one of those. Sometimes you have 3 components. You hold 2 components constant and vary only one at a time. Vary only one component on the reactant side at a time. When I say vary the component, what am I talking about? I said the variable is the concentration effects. Typically it's double concentration. And see how the rate changes. When you finish that one, then you hold the other constant and you vary it, and you draw your conclusion about what the trends are in the rate law. And we went over those last time, and you recall if it's concentration is A, your change in concentration is 2A, and your rate change and your change in rate, let's put it that way, your change in rate is 0. This gives you a 0 order reaction. If you start out with a concentration and you double your concentration and the rate doubles, then you have what is called a first order reaction. If you double your concentration and you go up 4 times, this typical problem effect, then what you'll have is a second order reaction. Okay, so you look in the data and you try to make those decisions about how the rate changes as you change concentration. So let's look at this first one here. Okay, we're given 2NO as a gas plus O2 as a gas goes to 2NO2 as a gas. All right. Okay, in the experiment, and I'll try to do this one out. 1, 2, 3. We have a concentration of NO, and they're all gases. O2 gas, and then you have a rate, and it's in moles per liter per second. So that is 0.0125 and 0.0235 and 0.0281 and 0.0250 and 0.0253, sorry. Okay, and that gives you 0.112 mole per liter per second. The third one is 0.0125, so we're holding that one constant now. And then we'll go to 0.0506 molar, and that gives us a 0.561 rate. Okay, so the idea is to determine the rate law of this Okay, when that question is asked, what is the rate law or determine the rate law, we start with the empirical rate law, and that's always in terms of the reactant side. And we write it empirically like this, in which you have unknowns and, of course, the rate constant listed. The x and the y are values you are to determine from the experimental data. So if we wanted to do NO first, NO right here, we would change its concentration while holding oxygen constant. So this one is a constant right there, but we double that. Now we look at what happens to the rate of reaction here. Now, if it's not immediately obvious, you divide the little number into the big number. And this will come out 3.985. We round up to 4 times. So the conclusion is X, which is associated with NO, will be a 2. Okay? Now we turn around and we hold we want to do the oxygen, but this time we want to change colors so you can see. Okay, we're holding this one constant. Well, that didn't work. I got one. So now the constant is the NO, and we go 2x on the oxygen, and so now we want to see how that one changes, and it's a little obvious. It's a 2x, so we double concentration, we double rate, so Y now is a first order reaction. Okay, hang on. I keep forgetting that. Okay, we'll just record it all. If we start out with one component, A, okay? In this case, a component, NO. and it has a rate for that concentration right there. Okay? It's 0.0281. That's rate 1. Now, I double the rate concentration. See, I double the concentration on that component. Okay? It gives me a new rate. Rate 2. How did that rate change? Went from 0.0281 to 0.112. Isn't that a 4 times increase? See what I'm telling you? Divide the little number into the big number. It's a 4 times increase. The conclusion, if you double and you get 4 times increase for a doubling concentration, you assign a 2 in the rate law. And you do the same thing with the other one. You double, see how we double the concentration in this one? And but we only observed a doubling of rate. That's all it is. And then you have to know this, though, this little table right here about the changes. And then look back over that from the first lecture if you need to. Okay, the last part of this is once we get this far, we saw for the K value to get the rate. First power. You can take any row. Hear what I said? Any row. Because constant's a constant for any row. Okay, so your rate, I'll take the first row, and you do the others and prove it. 1 mole per liter per second, like that. All right, then NO is 0.0125, and we have to square that concentration in the equation, in the rate constant equation, and 0.0253, like that. And this will all come out in molar cubed in the denominator. Molar, molar, molar squared, 1 cubed. Okay? And so like that. Y'all back me up on this if you would, because I'm writing so fast sometimes I kind of outrun my reasoning. So the numerical rate equation or rate law is now equal to 7108 minus 2 dot seconds minus 1 NO squared O2 to the first power, like that. So that's what they're asking for in that issue. Okay? Let me set up another one because we're out of time. I'm out of paper too. Nice how things work out, isn't it? Okay. I'll just set this one up for you. Okay? How do you set up the empirical rate law here? Let me get this pencil. If I'm going to set up the empirical rate law, I'll say rate is equal to K onto ClO2 minus to the X power or A, B, C, whatever you want to use, OH minus to the Y power. Now let me emphasize something here that I may not have said enough to stick to the wall, if you will. Just because the coefficients are 2 does not, in the kinetic region, mean that the X and Y will be 2. Only in the equilibrium region are the coefficients the same. But in the kinetic region, you have to determine X and Y experimentally, and only experimentally. Please check mark that in your notes. Okay. So what's the rule? Hold one constant and vary the other, and see how the rate changes. So here is, and you don't. The order of these experiments is not just automatically one concentration, two concentrations, three concentrations. They put them in any order. There'd be multiple orders here. So it's finding two where the concentration is doubled or tripled or whatever. In this particular one, if you'll notice, the concentration is 3 times. So you have to figure it from a 3 times concentration, and what does the rate do here? Okay, goes from 0.02 to 0.06 is a 3 time increase. What does that? Is that about 9 times?
Yeah, it's 9.
9 times? Yeah. About a 9 times increase. Well, what does that mean?
Third order?
Second order. Exactly right. So the trend in a second order, if you have to go back to the first lecture now, if you're not reviewing them, I encourage you to do so. A 2A concentration gives you, say, a trend of rate 1, then it jumps 4 rate 1, then it jumps 9 rate 1. That's a second order reaction. It's a trend. You have to learn the trends. If you don't know the trends on changing concentration, double concentration, what happens? Triple concentration, what happens? A double concentration would have given us a 4 times increase. But this one showed a triple concentration. And so our conclusion is a second order reaction. So this is going to come out 2 there. And here is a triple, and here's where the constant over here for this one. But here's a 3x, and what happens to the rate goes from here to here. We triple, and it looks like this is 3x also in the rate. So if you take 0.00276 times 3, I bet you get that number. So if you have 3 times a jump in the rate, then the issue is a first order reaction. So there is. Then you solve for K, divide both sides by the given value. Is now ClO2 minus squared OH minus, rate is equal. Take any row and plug into that expression to get your numerical value for the